Hello, my name is Andy Coluccio and I'm a student researcher at the University of Virginia. In this video I'm going to explain a method for markerless facial projection mapping, and we're going to walk through different software solutions used and how they tie together to create a projection mapping effect. Before we begin, I want to acknowledge a few folks who were very helpful as I was working on this project. First, Eamonn Farrell, my mentor for this project. I'd also like to thank Dino Mazza from Cast Software, who was very encouraging as I was working on this. I'd like to thank John Meehan from Panasonic, who was helpful when I was trying to get a sense of how this method is done at the industry level. And of course, I'd like to thank Jonathan Kokotajlo, a longtime collaborator who was very helpful in the 3D environment and simulation techniques that we were going to use in this tutorial. The markerless facial tracking program was created on the Intel RealSense SDK 2.0, and so I'd like to thank Marty G from the community forums for his help as I was acquainting myself with the SDK. In this video, I'm going to walk through the different components of the facial mapping projection software, both from facial capture to 3D manipulation in Blender, and ultimately off to a projection in Isadora. And we're going to break down each piece from the perspective of somebody who might not be a coder, who might not be very comfortable in a software C++ environment. I'm going to just try to explain with basic visuals and graphics how this works so that you could adapt it for yourself. I'd also like to mention that this project was completed for a showcase event end of term at the University of Virginia. And so if you were to scale this to a professional setting, there would be a couple of changes you'd want to make, and we're going to talk about those as well. There have also been some important developments on both the Intel RealSense SDK and Blender that would change the way I would approach this project, and I'll mention those as we encounter them. So without further ado, let's get into the tutorial.
So now I'm going to jump into a screen capture where I'm going to demo the rest of this. So let's start with an overview of markerless real-time facial mapping, kind of the methodology for how this is going to work. So we're going to start off with a RealSense sensor. For this tutorial, I'm going to use a D435. All right, and that's going to give us a depth frame and a color frame, and we're going to do some stuff to that. We're going to basically find where these facial landmarks are based on this information that the sensor is going to give us. All right, then we got to send that over to Blender, where we're going to have a 3D model of the face. And we're going to do some stuff to the face. We're going to texture it with a video perhaps, or maybe we'll put some lights in the scene or something like that. And so we're going to use this tracking information to modify this 3D model, plus our other things that we're doing in the 3D environment. And then we're going to capture that and send it over to Isadora, which will send us out to a projector. Okay, so let's start by talking about how the RealSense environment is going to work. So again, this D435 sensor, it creates both a color frame over here and a depth frame over here. And it has this cool function where you can align the two frames together. You can see there's a bit of distortion between the two of them based on the lenses that are used. You can combine them here, and then we can use something called dlib, which is an OpenCV wrapper, and it can draw these facial landmarks on the face, so it can detect the location of these faces. And then we're going to query all of them, so there's 68. We're going to query 68 of these tracking points and find out what their XY location is on this aligned frame that we have, and their distance from the camera represented by a Z value. So to help explain how that works, I'm going to launch this program called RealSense Viewer. All right, and let's take a look at how this works. So I'm going to ignore that. All right, so if I turn on my stereo module, you can see me now in a 3D environment. And if I hover over any part here, so I'm going to look over my cheek right now, you can see that I'm 0.5857 about meters away from the camera. Meanwhile, the microphone over here is 0.33 meters away, and the back wall is 2.3 meters away from the back wall. So basically, we're going to find our tracking points, and we're going to do the same thing I'm doing right now with the cursor. We're just going to ask how far away is that tracking point from the camera. Now, it's going to be important to keep in mind that the way this works, if I switch over to a 3D environment, is you can see that the world sort of consolidates to the single point of the camera. And this is an optical property, right? So if we had a sensor that was the size of my room, we could kind of directly map every pixel to every, square inch or whatever of the wall if we had an enormous sensor. But nobody has a sensor like that. Everything compresses down to a much smaller sensor. And I think that in this case, we're using something like a 3mm sensor. So real small, okay? So we have to get the whole world down into this size. And so we're going to use an optical property that's going to essentially take all that light and through the lens, it's going to focus it down to one point, and that's where the sensor is. So we're going to have to keep that in mind when we try to reconstruct this in the 3D world, that's what's happening here to capture all this depth information. Okay, so with that aside, we're going to now know the location of 68 tracking points on this face, and we're going to send that as an OSC command over to Blender. Now, if you're not familiar with OSC, it's Open Sound Control. It's a standard used a lot in theatrical context. It's a bit old. It's similar to MIDI in many ways. But here's a quick explainer of what OSC is. So it's a series of slashed enumerated messages, essentially. So for our tutorial, what we're going to do is we're going to use our first piece here. This is going to be the channel number. So I'm going to call it landmark, 0, 1, 2, whatever landmark I want to do, which corresponds to the numbers on this face, offset by 1, because in computer science, we start counting at 0, and this image starts counting at 1. Okay, and then we're going to send, in the rest of the message, we're going to have slash our X position, slash our Y position, slash our Z position. I've marked here this pixel, and depth, right? Because this is going to be the X, Y position in terms of pixels on this image here. So, maybe 200 pixels. If we're looking at the nose here, maybe it's like 200 by 300 or something like that, right? Okay, and then the depth value, which is going to be in meters. Again, so this is going to be how long along that diagonal line, right, that we had to draw to get back to the face. How far away was that? So we're gonna have to keep that in mind, because that's gonna be a bit annoying when we try to reconstruct that. So our commands might look like this. All right, this might be a section of our stream. Sending this landmark XYZ value, Z being in terms of meters and XY being in terms of true XY pixel values. So we might send a bunch of these over to Blender. All right, now Blender is going to have to interpret that and figure out what to do in a 3D world with these landmark information pieces that we're going to send over OSC. Okay, just to explain and maybe illustrate a little bit more about how this might work, I wrote an application. This is what I used in my demo. And if I turn towards the sensor just enough there, you can see it's detecting my face. It's drawing this green outline over my face. This is lifted right from a demo that I'll link in the description. And what we're doing is we're going to query some of these corner points, maybe the nose, maybe the piece of the eye here. And we're going to ask it, where does it appear in this XY plane? And also, how far away is this point from the sensor? So it's on you to develop a application that does this. Again, you're not locked into RealSense specifically. You could use any sensor just so long as it can be aligned to your pixel frame and figure out how far away that is. You could get away with anything, but I'm using RealSense for this demo. So I wrote this application that does it. There are better sensors out there that would scale different in a professional environment, but I had to pay out of pocket, and so I bought a D435, which objectively was the wrong decision. I probably should have gone with the D415 for a single face. The difference there is that a D435 uses stereoscopic infrared, whereas a D415 uses a coded light sensor. Coded light sensor is going to have less noise. This is a pretty noisy signal. You can see it's kind of bopping in and out of existence right now, and it could be that this light is messing with it in the background. But just to give a brief illustration, that's what we're going for here. Something that can track the face reasonably well. Works better in other lighting conditions, but you can kind of get a sense here. It can detect, as I'm moving around, I kind of get a sense there. So again, we're querying 68 points here, and we're sending that over OSC into Blender. Okay, so let's hop into the Blender side and explain how things are going on here. So you'll see right here I have this 3D model pre-generated. And I wanted to first start by talking about that. So you're going to need a 3D model, and ideally you'd be able to generate this real time or close to real time before the performance, right? So perhaps your performer sits in the chair and your program quickly creates this 3D model and ports it over to Blender. RealSense does sort of support this. The original SDK had a really helpful way for 3D scanning to work out, but then when they created the second version of the SDK, it didn't have that anymore. And I think the reason for that is that Intel is trying to move towards a middleware third-party solution versus just first-party implementations of all of these things. At the time that I was creating this program, actually, there wasn't any strong middleware for facial mapping. However, I got an email just a few days ago that suggested that has changed now. So your mileage might vary in terms of what you use. Again, ideally you generate this in real time, but there are disadvantages to that. For example, your model might have more holes in it. It might have a bunch of noise. It's going to require more cleanup and processing. Now you could automate that with a Blender script. Perhaps you could write something in Python that sort of is a catch-all, clean up the model and optimize it. But for my demonstration that I did for my final presentation, I decided that I was going to go ahead and 3D scan this face ahead of time, my performer's face, and optimize it and deal with all of that offline outside of the performance. And so I would just work with a nice model and not worry about all of these other hurdles that the SDK was bringing me. So there are many roads to get to this 3D model. A bunch of them have their own advantages and disadvantages. Obviously, if you get it ahead of time, you get more time to play with it. You can be more assured that it's reliable versus, dependent on performance lighting or whatever that situation is going to be. You could, create your media with the model in-house. Might be easier to do that than if you weren't really sure what kind of face you were going to get. But there are some disadvantages like scale and alignment that you kind of have to figure out if you choose to do this ahead of time. So many roads to get here, but you do need to find some way to generate a 3D model of your performer's face. The more accurate, the better. So the version of Blender I'm using right here, you can see, is Blender 2.79. Now, Blender 2.8 would be better because it has the Eevee real-time rendering engine. It's a game engine replacement for this Blender game, which is really outdated. So it's better for real-time work, but there are a few issues with Blender 2.8, stability issues. I had an issue with sort of getting Eevee to real-time render my video texture. And also, when I was developing this, 2.8 did not support animation nodes. However, that changed literally yesterday. So again, this is very much on the bleeding edge of things, and we're taking a step, regardless of whether or not the plank has been placed for us. So I went back to Blender 2.79. I do have this working on 2.79. However, I would push you to use Blender 2.8 once it is either released or becomes more stable or it works well enough to be able to get this done. So again, the two plugins we're using here are animation nodes, and we're using Add OSC. I'm going to start with Add OSC and how that works. So you can see over here, I've got 68 empties, okay? They're indexed 0 to 67, okay? So these empties are basically the equivalent of those tracking points that we saw earlier, this image here, right? So this is an analog to that, right, in the 3D environment. What we have to do here is bind these two key sets. So each one of these has a custom property. If I go over to here, you can see got this custom property: target depth, target X, and target Y. Okay. Now these are bound as key sets. So if I go over here, I can go to Add to Keying Set, and it'll appear over on Add OSC, and I can bind that key set to a particular value at a specific address, right? So if I was sending, again, back to our text example, if a particular command that I sent was landmark 0, 23, 7.246, okay, that would correspond here, where you can see that I have target depth in my key set, I have address landmark 0, okay, and I have index 2, so 0, 1, 2, so 2.46 would go in as the value here, okay, and then X would be the 0 value here, so at index 0 I would bind that value here for landmark 0, and then index 1 I have target Y, there so 7 would go in here. So this essentially is monitoring a certain IP address, right? So your program has to send it out. So I'm using the default software loopback and an input port 8000. These are just arbitrary. This address is a standard software loopback, and I picked an arbitrary port number that I knew wasn't going to be in use, and so that's hard-coded into the C++ program that is doing the facial detection and outputting the OSC commands. All right, so your situation will change based on what you choose to do there. But regardless, you're going to want three keys for each tracking point that you have. So if you do the math on that, right, if we're talking about 68 tracking points and three key values for each of those, you're looking at like 204 keying sets, and that's way too much for Blender to be able to handle in real time, at least on the 2.79 update. So my suggestion is to prune those values down to something a little bit more manageable. Okay, so I went in here, and this was my suggestion originally for which points we'd work. And I worked with Jonathan Kokotajlo on finding which points on here were actually worth tracking, and which ones were extra. Because you look at the full scale, right, and there's a lot of redundancy here. Perhaps not redundancy, but you get less information when you add 61, 62, and 68. When really all you really could use is 49. That gives you an approximation, right? You can figure out where the mouth is with fewer points. So my recommendation is to step it down to 20, which is going to be 60 values in the key set. Okay, so XYZ for 20 points. So just deal with 20 points. It makes your life easier. All right, and you just have to select those well. Also select them symmetrically for a few reasons that you'll see when we get into the animation node. So I'm going to pop over there and just give you a brief overview. So right now there are two scripts running on animation nodes. Let me first pop over to the tracking placer, okay? Now when you think about the issue of the data coming in, right? So we're giving it x, y, and distance values. Now, how the heck are you going to translate an XY position on a 640 by 480 image into some sort of 3D location in Blender? And that's what answers that question is what this first tracking placer does. And we're going to use a technique called ray casting. So over on the camera in the 3D view, and I think I might have it disabled, but there's a mesh that's sitting in front of the camera right now. And the mesh is a 640 by 480 mesh. All right, so we added that many vertices to the mesh. And essentially what's happening here is we're calculating a 3D position using an operation from a subprogram that was written specifically for this purpose that goes, a certain number of vertices over on the mesh and then a certain number of vertices down specified by the XY value, and then it raycasts it into 3D space to place this tracking point, this empty, in 3D space appropriately given the x, y, and distance value. Let me see where that calculation is completed. I believe it might be in this script here. Let's see. It's a subprogram that was written in. I'm not sure. Maybe one of these subprograms. Okay, I think it, yeah. Great. So you bring in your x, y, and d value, d representing the distance away from the sensor, and you do some math here to figure out, all right, where does that have to go? You do some scaling, and what this will do is it will project its depth to the empty. And those are the inputs and outputs of the function. Are going to essentially raycast this point from a 640 by 480 image, undo sort of that optical property we were talking about before, and place the empty in the 3D world. And that's really your goal. Okay, now the other script that we have here is some of the vector mathematics that are required to manipulate the 3D model so that it moves based on the correct parameters of these empties. So the first thing we have to do is find the average position of the face. So we're going to take all of the points that we're tracking. All right, we're going to add them up in a list. We're going to find the average, and we're going to move our, what we're calling here, better face, which is this facial model here, to that location. All right, we're also going to use that to place a normal vector. All right, so the normal vector calculation is a bit tricky. And what you have to kind of imagine here is that if we were to take a triangle, let's go over here. Let's find that image. Okay, so you remember the, good God. All right, so you remember the facial tracking points, and essentially what we want to do is triangulate a normal vector, calculate the normal vector between sets of 3 points at a time. And you want to do this symmetrically, all right? So if you imagine this facial model having sort of triangles drawn on it, you might have a triangle over here by the cheek, you might have a triangle connecting the eyes and the nose, all right? And if you imagine this in 3D space, there's going to be sort of an arrow pointing away from this cheek kind of into 3D space at a different angle than the one on this cheek, at a different angle than the one between the eyes and the nose, or the nose and the mouth. So you're going to get a bunch of these normal vectors, which you have to calculate. So the way that calculation goes is you input your tracking points, okay, and there's a node. There's a node for everything in animation nodes. It's really incredible. You calculate the normal vector from this pointless normal function. And again, the order does matter. You're using a cross product in the normal calculation, if any of you remember your linear algebra. And so it does matter what order you do that in. And I would suggest sort of adding in visualization points to make sure you don't invert a point accidentally or something like that based on the order. You have to be consistent. All right, then we're going to take the average of those normal vectors, and we're going to place kind of our master normal vector in that location. And that's essentially going to give us a normal for the face to point towards, to give it sort of an X, Y, Z position and a rotation value. Now there's one other piece to this that we need, and that's sort of illustrated here at the end. We need to apply some smoothing because our data is going to be noisy and we don't want the model to be flying all over the place. We want it to kind of smoothly rotate about. And so we're using a little bit of a trick here, this mixed vector and clamp value function. It's going to take the ultimate position that we just calculated up here and a second object, and that second object is going to move smoothly over to it with this clamping factor, so that it will move in 3D space kind of with a delay. And this will create a bit of lag if you're trying to do a real-time projection, but it's honestly worth it in my opinion. You can always scale these clamp factors to get that to work correctly, so that it will track smoothly, but also without too much latency. So that's really the gist of what's going on here with the animation nodes and with AddOSC. All right, now the last thing we have to do in Blender 2.79 is we have to trick the cycles rendering engine to advance our viewport view so that we can actually screen capture something. This is a bit ridiculous about how this process works. So for my demo, I used a video that I created custom for this face. So if I go over and select the face, you will see in the material view that I have a video texture created for it. Now, in order to view this in real time and something that you can screen capture and send over to Isadora, you have to unfurl this preview menu. Over here, you have to have a view of material, okay? And over here, you have to have a rendered view. All right, now when you do that, you can also go over here and you can select, you turn on your only render, turn on your world background, and select off of that, and you then play this video with AV sync enabled, and you'll see sort of these video textures apply to the face. That's what you want. Now the key is you have to have the second instance running down here in the full rendered view. That'll be, out of time, out of touch. So the way to do that is just to optimize your rendering as much as possible to avoid having any issues with playback. Okay, so you can see here I've got, clearly some 3D. The nose is up here, the cheek is over here. So you can see that this video is mapped onto the model. And again, this is much simpler in Blender 2.8. You just kind of click the right render and engine and go. But in 2.79, you have to play around a little bit more with it. I'll link a guide that sort of explains a little bit more detail about how this process works. But my ultimate suggestion is to, when you actually want to run this back, put everything on something really simple, something easy to view, maybe a file browser. All right, and leave that down here. And then have a second window, full screen. And this will be kind of what you track based off of. All right, so I'll leave this up here and I'll go ahead and start my OSC pipeline, leaving the old face up there. And so now you can see these values are going into OSC. And now if we look at that other Blender window and we play here, let's bring that back up. Let's go to a frame that has something in it. Right. You see that face is kind of moving around, and it's hard to get a good view about it because I don't have a whole lot of texture on some of these. But let's go to a piece like maybe up in here. Yeah, there's the face, and the face is moving around. It's a bit hard to see on the screen cap. Again, with optimizations, you can get this to run in real time, and that's the basic gist of things. Oh, I would also mention that if you're having issues with real-time playback, your optimizations aren't enough, you can go ahead and select AV Sync here. What this will do is it'll drop frames to get you back onto your defined frame rate based on your audio signal that's playing through. Just be careful if you change audio devices. That's what's happening right now, is that I launched Blender and changed audio devices. So AV Sync is being funky and dropping more frames than it needs to. Just a little quirk to be aware of. Again, lots of quirks going on here, really hacked solution to get Blender to adjust the 3D viewport with a video texture with, animation nodes running and moving empties around, and those empties sort of moving around this mesh in 3D space. Again, we're only really supporting here translation and rotation. We're not doing something like mesh deformation. That would be more complicated. That would require certain bindings that we just haven't supported right now. But when Blender 2.8 comes around, I'll probably re-explore that. And you're certainly encouraged to look into that as well. It could be an interesting expansion of this project. But for now, that's the basics of it. What you would then do is you would, capture this region here, or more accurately, you'd capture this second screen, okay? And this would go into Isadora, and then in Isadora, you would make some node adjustments to work with your real world, deal with lens differences, and account for all of that, and then take your result and project it out into the real world. And I'll show you a brief snippet of what that might look like now. Okay, so that kind of puts a bow on everything that's running here in order to get your custom C++ or Python or whatever base program you want to use that is querying these distance points and then passing them into Blender and manipulating in Blender and then passing off to Isadora. This is a sort of hacked together way to do real-time facial mapping. I would say that the real value here is this vector mathematics, so the method of calculating the normal vectors between different triangles on the face, and then using animation notes or something like that to figure out what the rotation of the face should be based on that. That will scale as you give it better input, less noisy input. The tracking will work a lot better. You have to be careful too about lighting conditions, right? Because what we're essentially doing is using dlib to create a facial detection of a region and trying to figure out what goes there. However, if there's too much interference, for example, if I have too many projections or something on my face, even in lighting like this, it's bopping in and out and kind of popping all over the place, and we don't want that. So what would be much more ideal is if there was a way to sort of train data sets to identify based on 3D data versus 2D data where faces were in 3D space, regardless of what that texture was. That would be more ideal, but RealSense does not support that right now. So again, we're using dlib just to sort of port those video frames over, do the facial detection, query based on the distance frame, do the proper alignment, send that over OSC to Blender, render the result, output it to a projector, and that's the current methodology.